Hi all, it's Mrs. Blasky. Today we're going to talk about electron configurations and how the structure of the atom can affect the attractions between those electrons and the nucleus. So first up, electron configurations. This is pretty much the exact same as we handled in first year chemistry. Actually, probably even a little bit different. You don't need to know the shapes of the sp, d, and f orbitals. You don't need to know the old dead white guys who did all the models of the atom. We are going to assume that we are sticking with the modern atomic model or the quantum mechanical model of the atom, where the protons and the neutrons are in the nucleus, and there's areas of probable electron density around the nucleus in those weird sp, d, and f shapes. What we are going to need to be able to do is to be able to describe the location of the electrons in a couple different ways. So the first way we're going to talk about is with electron configurations. So this is the exact same pattern as we learned in Gen Chem. A couple of rules that are followed. First is the off-bow principle. I always thought off-bow was a dude, but it's actually just the German word. So electrons always fill the lowest energy orbitals first. This guides us through the process of which orbitals are going to be filled in which order. This also accounts for this weird little dip and change in energy level between the 4s and the 3d, where it goes 4s, 3d, and then back up to 4p. It also accounts for the changes from the energy level in the f block. So D is always one energy level less than the S and P around it. F is always two energy levels less. It has to do with the size of those orbitals and the fact that they require so much more energy, so thus they're going to be farther away from the nucleus. Second rule that electrons always follow is that only 2 electrons can fit into any sublevel. For example, the S orbital has only 1 sublevel. A p orbital has 3 sublevels, and a d orbital has 5. We don't see f very often, but an f would have 7. We can have 2 electrons there, we can have only 1, we can have none, we cannot have 3. The Pauli exclusion principle states that electrons in the same sublevel have opposite spin. The idea of spin is not super important at this point, but it's more the idea that those electrons are not exactly the same if they're in the same orbital together. They have to have something that's a little bit different between them. So we draw that spin by showing arrows that either point up or down, showing that those are different when we do the pictorial diagrams of our electron configurations. And the last rule is Hund's rule. I call this the seats on the bus rule. Every electron is going to fill up a sublevel first before they start doubling up. Just like when you're on the bus, everybody wants their own seat before people have to start sitting with somebody that they don't know. So for example, if I have 3 electrons in a 2p sublevel, they're each going to spread out 1 in each sublevel before they have to start doubling up. They're not going to double up first and then start to go into the next sublevel. They're going to spread out first. I think the easiest way to remember electron configurations is just based on the periodic table. We've got an S block, which are the alkaline metals and the alkaline earth metals. We've got a P block, which are mostly the nonmetals plus a little bit extra. We've got the D block, which are the transition metals, and then we've got the F block, which are the lanthanides and actinides. And we follow along with those electron configurations straight up to figuring out where we need to be. So for example, number 3, says give the complete electron configuration for zinc. I gotta grab my periodic table real quick. Here it is. All right, so if I grab my periodic table, I find out where zinc is. Zinc is the last element in that 3D row, and so we need to fill in every orbital before zinc, including its orbital. So we start off 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and now zinc is in the 3d sublevel, and it is the last one in there, so it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10th. Interesting thing. Part B says zinc +2. If I've got a +2 charge, that means I have 2 less electrons. Now, when we have to decide which electron zinc is going to lose first, because of this weird energy level flip thing that happens here, zinc is going to lose its outermost electrons first. Those outermost electrons are the 4s, because that fourth energy level is farther away from the nucleus than that third energy level. So zinc +2 is going to be 1s2, 2s2, 2p6, 3s2, 3p6. You can either write 4s0 or not write it at all, 3d10. So that's sort of an interesting thing, that when we have those transition metals, they will actually more likely lose their s orbitals first. Those are actually their valence electrons that they will lose. When we talk about orbital notation, we're talking about drawing boxes to represent each one of those. And so for magnesium, we look at magnesium on the periodic table. It is in the 3s sublevel, would be its valence electrons. So we draw one box for the 1s. It gets 2 electrons, 1 up, 1 down. We draw a box for the 2s, 1 up, 1 down. 2p has got 3 sublevels in it. 1, 2, 3. Always get in the habit of drawing those spread out, because that's Hund's rule, that they have to spread out first. 4, 5, 6. And then I get to the orbital that magnesium's valence electrons are in. This is the 3s, and it's got 2 electrons in the 3s sublevel. So you guys can practice those ones. A little bit more questions about electron configurations. We know that we have some patterns with electron configurations. Things that have the same number of valence electrons tend to have some similar properties and behaviors. Topic 1.4 now, Coulomb's law. So this is something that we didn't spend a ton of time on in Gen Chem, maybe a little bit, but we're definitely going to be using it a ton this year. So all of our periodic trends that we're going to be talking about over the next couple of days can be explained using the idea of energy levels, the fact that those electrons fill up energy levels and they get farther and farther away from the nucleus, and Coulomb's law. And so Coulomb's law describes the relationship between the distance between 2 charged particles and the charge that each of those particles has. For our purposes, we are not going to be doing any math with this equation, but we are going to be using these relationships. So what this tells me is that the more charge something has, the more force those objects are going to have between them. This also tells me this distance is on the bottom. So the larger the distance between those items, the less force is going to be applied between those 2 charged particles. So for our purposes in chemistry, our charged particles are protons and electrons. And that distance between them is the distance between the nucleus and the electrons. What this means is that the electrons in the first energy level, which are physically closest to the nucleus, have the smallest distance, so they're going to have the largest force between the nucleus and those what we call core electrons, or the 1s electrons. The electron levels get farther away from the nucleus, they're going to not be as strongly attracted to the nucleus as those more interior, more core electron energy levels will be. This idea of Coulomb's law, we are going to use it to explain pretty much everything. So we're going to get to that in our next video. I'll see you later. Bye, guys.